Hello, today I'm going to show you how to design a non-inverting amplifier, and we'll go through the process of setting up a simulation model for it as well on LTspice. So let's get straight into it. A non-inverting amplifier is an amplifier where your input goes to the input pin marked with the plus, which is the non-inverting pin. So your input signal is applied to there. And you have two feedback resistors typically connected from your output to the inverting pin, and then another resistor connected to ground from the inverting pin. On this circuit you can see that the components are labeled RF and R2. The gain for this type of amplifier is very simple. A gain itself is how much the voltage changes per input, and we can calculate the gain for a configuration like this using the equation 1 plus RF over R2. Obviously, when we are designing the operational amplifier, we'll want to get a certain amount of gain from this device. In order to do that, we'd have to rearrange that equation so that we can calculate all the resistor values in the circuit. I've shown you an example on how you can do this for RF. So obviously in this case, you know what gain is. Let's say you fixed a value of R2 to something, and then that lets you calculate the value for RF. Another way you can do it is by fixing RF and then organizing the equation so that you get R2 by itself. Just a quick example for a non-inverting amplifier set up to produce a gain of 3. So it amplifies any input signal by 3. So first steps, obviously we've got the reorganized equation. We're going to fix the value of R2 to 20k, and then that lets us calculate the value of RF. So you can see I've put in all the values, so 20,000 times 3 minus 20,000. So R2 times the gain minus R2 equals RF. So this equation is telling me to get a gain of 3 from my op amp. If I have fixed the value of R2 to 20k, then for RF I need a value of 40k. Let's now try to build a simulation model of this circuit on LTspice to see how well it works. I will put up a picture of the circuit on the side so you can follow along. Obviously what we need is 2 resistors, a power supply, so I'm pressing F2 here to get this selection, then voltage source for the power supply. I'm going to put that on the left hand side. Now I'm pressing F2 again and going to op amps section, and we can select almost any, but they all do have slight differences on how they work. I'm going to go with LT1366 because this is an op amp I've used before and it should work okay. So we can see the configuration for the op amp. So we've got the non-inverting pin here, the inverting pin here and the non-inverting pin here. You've got the output pin here. You also have additional 2 pins here which are not shown on the circuit. These are the power input pins. So the negative can be connected to ground in this case, and the positive can be connected to the power supply. I'm going to set the power supply to 10 volts to begin with and connect this to ground. To get the ground symbol, a shortcut for that, you can use G. So just connecting up the circuit as we see it on the model or on the circuit schematic above. We need a secondary source to produce our input signal. So I'm just going to copy the first power source and change the voltage to, let's start off with a value of 1 volt DC. So this circuit, although you can see it's slightly different because of the way the pins are, but it's the same as you see on the schematic. I'm going to change the values of these two to the values we calculated. So that was 40k and 20k. We have an input of 1 volt. Our calculated gain was 3, so 3 times 1 should equal 3 volts. I'm going to add a load. This is just for simulation purposes. Might not be needed, but it can be helpful. So I'm just going to put a high value resistor here, and this is a load resistor. Could be your ADC or wherever this output is going to. So let's simulate. When we simulate on LTspice, we have to give in some parameters. For this one, I'm not too concerned, so I'm just going to say I'm going to simulate for 1 second. So that appears there, and then the simulation model can start. So now you can see the op-amp is working as we thought it would. I'm just going to change the scale on this graph so that we can see slightly better. As you can see, we are applying an input voltage of 1 volt, which you can see on the blue line, and we are getting an output voltage of 3 volts, which you can see on the green line. We can add net labels to this to make the graphs easier to read. So for example, I can say Vn, and I can change this to Vout. If I press simulate again, I will get the same things, but the labels will have changed to Vn and Vout. So now we can see we're getting an input voltage of 3 volts. Obviously, talking about some of the limitations of op amps. If I was to change this input voltage to -1 volt, what do you guys think will happen? So obviously, we've got a lower power limit of a ground, so 0 volts. So the op amp is not able to produce anything less than that. So you can see the input voltage is -1 volt, but the output voltage is saturated at 0 volts. So the op amp cannot go any lower. We can fix this by adding a negative power source to the circuit, which should hopefully fix the issue that we are seeing. And I'm going to do this with net labels. So you can see, go to net Vs minus, and I'm going to connect that here. And then I'm going to move the ground to the middle of this. So this means we now have -10 volt supply, and I'll show you that in the circuit, in the simulation model. So you can see we've got a -10 volt supply going to the op amp. If I now simulate this, we have an input voltage of -1 volt. -1 times 3 equals -3. So we should get an output voltage of -3 on this pin, which you can see we get. So that is saturation on the low side. We also get a similar effect on the positive side. So you can see we've got power supplies of ±10 volts. If I was to put down a voltage of 4, so if our input voltage goes up to 4, the output should be 4 times 3, so 12 volts. If I simulate this, you can see the output doesn't reach that stage, and it can only go up to 9.995, so it's about 5 millivolts away from 10 volts. So it's saturating at the positive power rail. So obviously that's a limitation. So we can either limit the input voltage to ensure that it never goes to that stage, or we can increase the power supply, if this is possible, to 15 volts. And then you can see the output is gone up to 12 volts. So your input is 4 volts, 4 times 3, you got 12 volts on the output. Thank you for watching. If you have any questions, please comment down below and I'll be happy to help.